All right. Welcome at long last to our calculus bootcamp for AP Physics C. Our goals today are going to be to enable you to evaluate elementary derivatives and integrals using the power rule. We'll talk about what that is, and contextualize their meaning in terms of graphs. So we'll talk about derivatives and slopes, the power rule for derivatives, what an antiderivative is, and talk a little bit about integrals. Now, I do want to note there you'll learn lots of different derivative and integral rules in addition to the power rule, exponent rules, all kinds of other stuff. We're just going to start with the power rule at first. So what is a derivative? Well, we're going to motivate this discussion, as we have previously, by considering a turtle. So here we have our turtle, Spooky. So let's assume that we've got some x equals 0 point, and we track Spooky's motion over time. And let's say Spooky makes this graph on an x versus t, on position versus time, right? So it goes to some positive position, goes back to 0, to some negative position, continues to some positive position. And we want to ask, what is Spooky's velocity here at t equals 0? Now, you might be able to read this graph and say, well, Spooky is moving in the negative x direction, so probably some kind of negative value. But what if I wanted it exactly? I wanted the actual number. I wanted 2, 4.5, negative 6. So I wanted the actual number. Well, what we could try to do is we know already that average velocity is equal to delta x over delta t. So we could try to calculate Spooky's average velocity. Now, what if we take these 2 points? So we'll take these 2 points and kind of consider Spooky's average velocity between them. And you'll notice that that doesn't do us a whole lot of good, because if I kind of connect these two with a little dotted line, I end up with something with 0 slope. Because remember, we're talking a little bit here about slope. Here I'm at position 0, here I'm at position 0. That's just not good enough. I check Spooky at 2 different times, here and here, and I don't get a good approximation for the value. So what can I do? Like we said in the other videos, we can make delta t smaller. We can zoom in on the moment in time we're actually talking about. So what if we take instead this time and this time? If we do that and we kind of imagine connecting them with a line, we get a line that's a little too thick. We get a line that's got a much more reasonable slope. It's steep, it's negative, but you'll notice it doesn't quite match up right around t equals 0, right? It's a little too shallow. Spooky's actual velocity at t equals 0 is a little bit more extreme. So what we can do is we can keep getting smaller. We can, use these 2 points and get a little bit more refined and a little bit more refined and a little bit more refined. And the closer and closer and closer we get to 0, the better and better we're going to do. So we're actually going to take those 2 data points that we're taking to calculate the average velocity. We're going to squish it down, 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 squish it down until we're as close to t equals 0 as we possibly can get. And what we actually get here in calculus language is we get what's called a limit. So we're actually going to ask, well, as I take successively smaller values of delta x over delta t, right? As I make delta t smaller and smaller and smaller, these numbers change. Here I got 0, here I got some negative, let's say negative 5, here I get, negative 7. I'm getting closer and closer to the real value. And as I make delta t smaller and smaller, I approach some value. And what we call, in calculus, we call this value a limit. As delta t approaches 0, as the time interval that we're using gets smaller and smaller and smaller, approaches 0. And this is what we're going to say is our instantaneous velocity, rather than our average velocity. It turns out taking limits like this is exactly what we do in calculus, and that is what a derivative is. So here's the technical definition of a derivative. The derivative, which you can write in a couple different ways. Here we're going to write it as f prime, as opposed to f of x, f prime of x. So the derivative at some point x0 is the same as the limit of the slope, delta y over delta x, as we make that run smaller and smaller and smaller. Again, that's like shrinking down our run super small. We can also write it as the limit this way of the value of the function at x0 subtracted from the value of the function at some later time, or at some later point, divided by that. And again, this is just rise over run, right? If we're going from this point to this point, that rise is just, here's our delta x. That rise is just the later value of the function minus the earlier value of the function. So you'll be doing this in calculus class, and maybe you already have a bunch. This is not how we're going to be doing it in this class. We're not going to have to use the limit definition, but it's still nice to know. What we're going to be more concerned about is that a derivative tells us two things. It tells us that instantaneous rate of change. So the derivative of a function tells us the velocity or the rate of change at a particular moment. It also tells us the slope of the tangent line to the graph. And a tangent line, if you're not familiar, is a line that just touches the graph. So over here, our tangent line is nice and flat because it just touches the graph like that. Over here, we're like this, like this. Over here, we might be like that. A tangent line is, if you kind of imagine putting your pencil flat along the edge of the curve or following the curve, it's the slope of your pencil. Now, and that's why we've been talking so much about slope. Now, there is some different notation here. Sometimes we'll use primes. So you'll see like, f prime of x as the derivative of f. Maybe, you could decide that velocity equals like x prime of t. You'll also see it written as dx dt. Or sometimes if you have y as, dy dx. And I just want to encourage you to think about this as turning a delta into a d. That delta y, delta x is when you have big chunky differences. But as your differences get smaller and smaller and smaller, and you narrow down on one moment of your graph, that your deltas kind of become derivatives. And the reason I want you to think about that way is that it actually makes a lot of sense if our average velocity is delta x over delta t, that our instantaneous velocity is just dx dt. Now, you can take derivatives more than once. And so this is why, your acceleration is your derivative of velocity, or you might say your second derivative of position. You can also write, acceleration is going to be x double prime, the second derivative of x. You will also, once in a while, I love this because I'm a math and physics person. In physics, specifically when you're talking about time derivatives, sometimes you'll see two little dots, but we'll get there. All right, so lots of different notations, some primes, some d's, different things like that. How do we actually take derivatives? Because for most of you, this is what you actually want to know. We're going to stick for the moment to polynomials, to something to the something power. We'll get to more complicated ones later. So the power rule goes like this. If I want to take the derivative of something that looks like some number a times x to the n power, what I do is I grab the power, the exponent, and I multiply it out in front. So I get a times n, and then the exponent gets incremented down by 1 to the n minus 1. So as an example, let's say my original function is f of x equals 4x cubed minus 2x to the fifth. I can instead turn f prime of x, right, my derivative. I can take this 3 down. 4 times 3 is 12. And then remember, I got to subtract 1 here. So 3 minus 2 is 2. So 4x cubed turns into 12x squared. Minus the 5 comes down. I get 10x to the fourth. As for why the power rule works, there's a really cool video by my favorite math blogger, 3Blue1Brown, that has some good explanations of this, but that's not germane to the class right here. Note, this x can be kind of any variable. So if I want to take a derivative of x with respect to time here, I can just kind of be like, oh, well, okay, there's a t here, but that's okay. I'm going to still take the 3 and bring it down. I get 3t squared. Now, remember that 2t is secretly 2t to the 1 power. So I can kind of bring the 1 down, and I just get 2 times t to the 0, reminding ourselves that, generally speaking, anything to the 0 power is 1. So 2t to the 0 actually just becomes 2. And then a peculiar thing happens with the 4. The 4 actually goes away. The 4 actually goes away. And the reason the 4 goes away is, imagine I had this function, right? Imagine I had the function f of x equals 4. Ready? I'm gonna draw f of x equals 4. There's the function f of x equals 4. And you might ask, what's the derivative of that? How much? Well, first of all, how much does it change? It doesn't. It's always equal to 4. You also might ask, what's the slope of this line? The slope is, of course, 0. So whenever you take a derivative, constants go away. Constants turn into zeros. So t cubed minus 2t plus 4 turns into 3t squared minus 2. All right. So that's how you do derivatives under the power rule. Like I said, there's other rules. So now let's talk about the flip side of this, the integral. And I'm going to motivate this by saying, let's say we have a particle moving with a speed according to the function v equals 3t squared. So I can always ask myself at, whatever time, how fast is my particle going, etc. What's the acceleration of the particle? Well, we know that the acceleration is the derivative of velocity, so I can go ahead and do dv dt and get 6t. That's great. What's the position of the particle? That's a little bit weird. I don't know how to do that yet. Because what I'm trying to do is I actually want to do an antiderivative. I want to do the opposite of a derivative. Because I know whatever my position function is, that the derivative of that function has to be 3t squared. So the question is, what kinds of things have a derivative 3t squared? So let's play a little guessing game. If f prime of x equals x, what could f of x be? Well, we know that this is kind of like x to the 1. And if we think about our power rule, right, for derivatives, ax to the n equals nax to the n minus 1. If I take my derivative and I end up with a 1 here, this is 1 smaller than it started with. So my f of x probably needs to look something like x squared. The problem is x squared doesn't work, because if I check my answer, if I take my derivative of x squared, the 2 comes down and I get 2x. And in fact, that's kind of the answer here. If f prime of x equals 2x, f of x could just be x squared. So what do? X squared doesn't work. Well, remember, I can have a factor that I multiply in. So what can I use to get rid of a 2? I can use a 1/2. So now I get 2x times 1/2. Those cancel, and I just get x. So the antiderivative, the antiderivative, the opposite of a derivative, the antiderivative of x is 1/2 x squared. Similarly, if I have 2x, I can get just x squared. If f prime of x equals x squared, I could follow the same logic and say, well, it's got to go up by 1 if I want to do the opposite of a derivative. A derivative takes us down by 1. The opposite has to go up by 1. So I'll get an x cubed. That's not going to work. I'd get a 3x squared, so I can cancel it out with a 1/3. And this is the concept of the antiderivative. We have our power rule for derivatives. The antiderivative is also sometimes called an integral. So that's an important note. An antiderivative is an integral. That is what the integral is. It is the opposite of a derivative. It also has some other things. So we do have a power rule for integrals, which tells us that the integral of ax to the n dx is given by this. What you do is, again, the opposite of an integral. You make your exponent go up by 1, and instead of multiplying by the exponent, you divide by n plus 1. Now, we'll talk about this plus c in a second. Don't worry about that. So don't worry about that. So you could say that the integral, say, of 4x cubed with respect to x, and we'll talk about what that dx means, but for the moment you can read it as with respect to x, is going to be, let's see, 4 over, well, my exponent was 3, so it needs to be a 4, and then I need to do 3 plus 1 is also 4. So I get x to the 4th. And sure enough, if I take the derivative of x to the 4th, I get 4x cubed. If I want the integral of, say, 3x squared, no, I don't want to do 3x squared. That's too boring. 7x squared minus x to the 6th dx. 7x squared will become 7/3 x cubed minus 1/7 x to the 7th. And you do actually get a plus c afterwards, and we'll talk about where that comes from. I will post up if you look at your AP Physics C formula sheet, that both of these rules are in there. So here, let's talk about Spooky. Spooky moves with a velocity function of 40t minus t squared. What is her position over time? So here we're going to take an integral. We're going to take an antiderivative of 40t minus 6t squared with respect to t. And what we can do is we can then say, okay, well, 40t has to become t squared. But I also have to divide by 2. To make sure that this squared exponent doesn't mess it up when I take the derivative again. So that's going to be 20t squared minus, let's see, 6 over 3t cubed, or 2t cubed. And I'm going to get this plus c plus some constant number at the end. And again, if I take the derivative, I can check, and I get 2 times 20 is 40, 3 times 2 is 6. And so here's the question about that plus c. So let's go back to this f prime of x equals x. And I told you that, we could take the integral of x dx, and we could get 1/2 x squared. But is there more than one choice? What if I do 1/2 x squared plus 1? If I take the derivative of 1/2 x squared plus 1, I get, let's see, power rule for derivatives. The 2 comes down and cancels out the 1/2. I get x, and then the plus 1 just goes away. The derivative of a constant is 0, so I just get x. What if I have 1/2 x squared plus 2, or plus 77, or plus pi? It turns out that any constant you add here doesn't matter. You end up with the same derivative. And so we actually have to remind ourselves when we take an integral that we have to add back in that plus a constant. And the reason you get that is that information gets lost when you take a derivative. One consequence of this is that integrals only tell you about change. They don't tell you where you start or where you end. Sometimes you need some additional information to put in there. So like on our previous question, we say we add this extra information that she has to start at position 0 at time 0. And that can help us figure out what c is. All right, so if I plug in x of 0 should be 0. See, I get 20 times 0, 2 times 0 plus c. All right, so in this case, c was equal to 0. So as we'd said, sorry, we had a little break in the video. So just to recap where we were, noting that we do have to add that constant term in because, again, 1/2 x squared plus 2 is the same as 1/2 x squared plus 7 or minus pi from the perspective of a derivative, right? These all have a derivative of x. So when we take that integral, we do have to remind ourselves that there's this mystery factor. And we can use extra information in our calculations, in our problem, to figure out what that is. These are what are called indefinite integrals. They don't have numerical bounds. They're just kind of turning one function into another. We do have a second kind, which let us calculate the area under a particular curve. So let's say I want the area under this particular curve. It's bounded below by y equals 0, and above by this function y equals f of x. And I want it between x equals a and x equals b. I just want some section of it. Well, in general, it's kind of hard to find this area. So what we're going to do is we're going to break it down. We're going to cut it into little rectangles. And you might be saying to yourself, Mr. Bates, why are you making little rectangles? This thing has a curved top. If I make little rectangles, I'm going to miss some of the area. And I'm going to say, hush, worry about that later. So I'm going to cut it into all of these little slices. And I'm going to give each slice a little width that I'm going to call dx. So these little rectangles are dx on the base. And you can kind of look and see how tall they are. And how tall are they? Well, they go up to the height of the function, f of x. They touch it right at one point. So what we can do is we can say the area of one slice, is just going to be f of x times that little width dx. And if I want to add them all up, my total area, I've got to do a sum. I've got to add up all of these little slices. Now, you might again remind me that, Mr. Bates, hey, look, we've got missing area here. There's little extras that we're missing. And my response to you is, oh, that's okay. I'm just going to make my slices smaller and smaller and smaller. I'm going to pack more and more and more into them. I'm just going to cut it even more carefully. And that's going to make that error get smaller and smaller and smaller. And in fact, we're going to end up with a limit as I make my slices infinitely small, as I get an infinite number of slices. And then my sum, instead of this Greek letter sigma, this Greek letter s, turns into a big letter S. And I'm going to write this as the integral of f of x dx from x equals a to x equals b. And this is what's called a definite integral. And it yields the area under the curve. Now, it's very similar to an indefinite integral. It's very similar to an antiderivative, but there are a couple small details about how you do them. So what you do, this is the fundamental theorem of calculus, is that if you want to evaluate a definite integral, what you do is you first take the function, in this case they've got the function little f, and they say find the antiderivative, which is, in this case, they're going to call it big F. Find the antiderivative. And then you evaluate it at the endpoints. If our integral is from a to b, you evaluate it at b, you evaluate it at a, and you take the difference. Which again kind of reminds you of a little delta. It's a little final minus initial. Tell you about change. So let's try this. Let's find the area under the curve of f of x equals x squared between x equals 1 and x equals 2. Well, I can set this up. This is the integral from 1 to 2 of x squared dx. Well, I know how to take the antiderivative of x squared. That's going to be 1/3 x cubed. And I can run this from x equals 1 to x equals 2. And now what I do is I've got the antiderivative. I plug in 2. I plug in the later endpoint, 1/3 times 2 cubed. And I subtract away 1/3 times 1 cubed. And what I end up with is, let's see, this is 8/3 minus 1/3. So I guess that area is exactly 7/3. And now you might ask me a question, Mr. Bates, what happened to the plus c? Well, imagine that I had left the plus c in there for some, I don't know, let's say c equals 1. I would have ended up with plus 1. I would have ended up with then 1/3 2 cubed plus 1 minus 1/3 times 1 cubed. Plus 1. And you can still see the ones would have canceled out. So when you're doing definite integrals, you don't have to worry about plus c. We can also use symmetry to make our lives easier. If we're taking the area under a curve like this, we can actually split it in half, do the integral of only 1/2, and then multiply it by 2. All right, so hopefully this was helpful to you. I just want to remind us that now we know how to do simple derivatives and simple integrals. There are other rules if you want to like take the derivative of like sine x and things like that, which happens to be cosine x. But there are other derivative and integral rules out there in the wild. For the moment, we're going to be sticking to polynomials.